Greetings everyone! Today I've got 3 example problems for you, all on angular momentum. The first one is about a merry-go-round, the second one is about a firefighter, and the third one is about a neutron star, my favorite. First question is a nice one about a not evil merry-go-round, unlike Pennywise's merry-go-round from the beginning of the semester. We've got a 30-kilogram child here running towards the edge of a merry-go-round. This is a top-down view of a merry-go-round. If you don't know what I mean with that phrase, look on the slides for the merry-go-round and you'll see what it is. But it's a disc that can spin in the middle. So the child is running at 4 meters per second towards the edge of this disc that rotates in the middle. The disc has a radius of 1.1 meters and a mass of 150 kilograms. We need to find the final angular velocity of the disc of the merry-go-round and the final velocity of the child. Well, what kind of problem is this? This is an angular momentum problem. Should I say delta L equals 0? Well, that's going to be true if there's no outside forces acting on this, outside torques, excuse me. Are there any outside torques? Well, there could be maybe a little bit of friction there in the spinny thing, but I never mentioned anything, so we're just going to assume that there's no outside torques. So delta L is equal to 0. That means that L initial is equal to L final. The initial angular momentum is equal to the final angular momentum. What is causing the initial angular momentum? The disk is not spinning in the beginning, and neither is the child. Neither of these are spinning. So where is the angular momentum? Remember this weird Lego contraption? Well, this thing isn't spinning, and my fist isn't spinning, and yet I can make it spin by hitting it. Nothing was spinning in the beginning, but by hitting it, I can make it spin. We are going to use the exact same principle to solve this problem. The child is running in there at a great speed and going to jump onto this rotating disc, and is that going to make it spin? I hope that we've all played with this kind of thing because it's kind of fun. So I hope you all know that running at it and jumping onto it will in fact make it spin. Now, we need to have momentum, angular momentum initial for the merry-go-round, which I'm going to have as m, plus angular momentum initial for the child is equal to angular momentum final merry-go-round plus angular momentum final child. Does the merry-go-round have angular momentum in the beginning? No. All right, what are we going to use for the angular momentum initially for the child? We are going to use R cross P. That is the initial angular momentum of the child. That is going to equal the final angular momentum of the merry-go-round, which is spinning, as we discussed, at the end, plus the final angular momentum of the child, who has jumped onto the spinning contraption like that, or jumped onto the contraption which made it spin. So what equation are we going to use for that? I think we can use I omega, specifically I of the merry-go-round times omega final merry-go-round, plus I child omega final child. What can we say about the final angular velocities? Well, if the child has jumped onto the disk and that made it spin, well then the child is spinning with the disk. Therefore, the final angular velocity of the merry-go-round should equal the final angular velocity of the child. We can get rid of this and that right there because they're equal to each other. What is r cross p? R cross p is r cross mv. And these are all vectors. Now, what else can we call this? I'm going to skip another line. This can also be r mv sine theta. r mv sine theta, the cross product will often just turn into the sine of theta. Always in this case. Now, what is the sine of theta? What is theta here? Theta we can determine by finding our center of rotation there, drawing a line from our center of rotation out to where the force is being applied. Now, if the child runs onto the merry-go-round and jumps onto the merry-go-round right there, then that is where the force is being applied. So we draw our line from the center of rotation out to where the force is applied, and then we look at where the momentum is pointing. The momentum is pointing this way. The child's momentum is pointing like that. So we draw our angle between this radial line r and the v for the child. And that is a right angle right there. Right angle, sine of 90 is 1. This is going to equal the moment of inertia of the merry-go-round times the final angular velocity of the merry-go-round plus all that. So what's the moment of inertia of a solid disk? This is one of the things that you'll probably end up memorizing by accident. It is 1/2 mass merry-go-round radius merry-go-round squared plus, oh, sorry, this is times omega final, so omega final. Then plus moment of inertia of the child. Now, what is the moment of inertia of the child going to be? The child is not a cylinder, hopefully not a sphere, hopefully not a thin-walled hollow sphere. What is the moment of inertia of a child? Remember when we first started talking about moment of inertia, we said that any object which is being rotated around an axis that does not go through it is going to be just mr squared. So the moment of inertia of the child is just mass of the child times r. Now r is the distance to the center of rotation. The distance to the center of rotation is just the radius of the merry-go-round. So this is rm squared. So this is the moment of inertia right there for the child when the child is being spun around an axis that does not go through the child. The axis goes straight down there, but the child is over here rotating around. Thus, the axis does not go through the child, so we're just going to call it that, and this is times omega final. What's this m over here? That is the mass of the child. What's this r over here? That is the radius of the merry-go-round. And what's that v? Well, that's the 4 meters per second. We do get to cancel some things out. The radius of the merry-go-round is everywhere, so we can get rid of one of those as long as we get rid of one of those and one of those. We can't get rid of the mass of the child because it's not in every term. But we do know a lot of this stuff now. So on the left-hand side of the equation, we've got the mass of the child, which is 30 kilograms, times 4 meters per second. And that gets us 120 over here is equal to, I'm going to factor out this omega final times this stuff plus this stuff. So that's 1/2 times mass of the merry-go-round, 150 kilograms, times radius of the merry-go-round, 1.1 meters, plus the mass of the child, 30 again, times the radius of the merry-go-round, 1.1. And we get 115.5. Then we can solve for omega final, and that's just going to be 120 divided by 115.5, which is 1.04 radians per second. My follow-up question is, how fast is the child going on the edge of this merry-go-round? Linearly, tangentially, I should say. What is the tangential speed of the child on that merry-go-round? Well, tangential speed, omega is equal to v over r. Omega, we already know, is 1.04 radians per second. That's equal to the v that we're looking for over 1.1. So we can just multiply both sides by 1.1. And we get that the velocity of the child at the end is 1.14 meters per second. That's interesting. The child had been running at the merry-go-round at 4 meters per second. But after the child jumps onto the merry-go-round, the child is only traveling at 1.14 meters per second. The child slowed down a lot, but the merry-go-round sped up a lot. The merry-go-round was going at 0 meters per second. The edge of the merry-go-round was at 0 meters per second or 0 radians per second at the beginning of this. So the child lost a lot of velocity, but the merry-go-round gained a lot of velocity in this exchange. We can definitely think of this as a collision problem. If you look carefully, there is nothing here that's really any different from a collision, a linear collision. We've got delta L is equal to 0 instead of delta P is equal to 0. Initial angular momentum is equal to final angular momentum instead of initial regular momentum is equal to final regular momentum. The one weird thing is this, that we can convert one of the angular momenta into a linear momentum times a radius. That's the one thing that makes it not quite a momentum problem. But looking at the skills that you use to solve momentum problems, these are all the same skills, except here's the one new skill that you also need to remember. But everything else kind of works out effectively the exact same way. Next question, in many ways similar to the last question. We've got a firefighter who has a mass of 75 kilograms. And he's running towards the side of this door. This is the overhead view of everything. So that's supposed to be an overhead view of a firefighter, and that's an overhead view of a door, I guess. Well, the firefighter runs at this door, at the edge of the door. The door swings around that point. And I tell you that the initial angular momentum of the firefighter is 240 kilograms meters squared per second. That actually solves a whole bunch of the problem right there. The firefighter slams into the door, and the door is inexplicably sticky. So the firefighter is going to get stuck to the door, and the firefighter and the door together will swing open that way. The door will swing open that way with the firefighter stuck to the door. I don't know why. The door is 0.8 meters wide, and the firefighter is going to hit the edge of the door there. And the door is 2.1 meters tall. And we need to find the angular velocity of the door plus the firefighter together, and the time that it takes for the door and firefighter together to go 90 degrees. Open up 90 degrees. Like that. Now, what kind of problem is this? Well, this is another angular momentum conservation problem. Delta L is equal to 0. L initial is equal to L final. L initial firefighter plus L initial door is equal to L final firefighter plus L final door. Well, does the firefighter have initial angular momentum? Yep. Does the door? Nope. Do they at the end? Yeah. So we've got 240 because I gave you that number, is equal to angular momentum of the firefighter at the end. Well, that's going to be the moment of inertia of the firefighter times omega final. They're stuck together, so they're going at the same angular velocity, plus I door omega final. 240 is equal to moment of inertia of the firefighter at the end of the problem. Again, that's just a point-like object at the edge. So the firefighter is going to be over there, but it's spinning through this point, and so we can just use mass firefighter radius squared. And what radius is that? That's actually the width of the door. So I'm just going to write d there, because that's the distance from the point-like object to the center of rotation. And this is times omega final. And this is plus the moment of inertia of the door. Well, we need to figure out what the moment of inertia of the door is going to be. And for that, we need the book again. Which one of these looks most like a door? Well, one of these looks like doors, or these both look like doors. Now, when you open a door, does it spin through an axis that goes through the middle of the door like that? Imagine that this is a door. Like that's where the floor would be, that's the side of the door, and that's the top of the door. Is the door going to just start spinning through an axis that is going right through the middle of the door? I really, really hope not. If that's the case, you live in a haunted house. You need to move out. I hope that you live in a house where doors open by the hinges on the sides of the door instead. In non-haunted houses, doors will open on an axis that goes through the edge of the door. I'm going to assume that this is a non-haunted house that the firefighter is in. And so we've got the moment of inertia is 1/3 ma squared, where a is the width of the door, which is 0.8 meters. B is the height of the door. Does that matter at all? No, it doesn't. So we just need 1/3 times the mass of the door times the width of the door squared. So 1/3 mass door radius door squared omega final. 240 is equal to the mass of the firefighter, 75 kilograms, times the radius of the door, 0.8 meters squared, time, I'm going to factor out the omega final, plus 1/3 times the mass of the door, 35 kilograms, times the radius of the door squared, 0.8 squared, all times omega final, because I took that out. We can calculate this. 75 times 0.8 squared plus 1/3 times 35 times 0.8 squared is going to be 55.47. So 240 equals 55.47 omega final. We can divide 240 by this thing, and we get omega final is 4.33 radians per second. 4.33 radians per second. Is that a lot? I don't know. Well, let's find the time that it takes to go 90 degrees. That's a bit easier to think about. Now, what is 90 degrees in radians? 90 degrees in radians is pi over 2 radians. A full circle is 360 degrees, or 4 times that, and a full circle is 2 pi radians. So divide the 2 pi radians by 4, and you get pi over 2 radians. Pi over 2, 3.141 divided by 2, 1.57. If we're going at 4.33 radians per second, and we need to go 1.57 radians, how do you calculate that? How do you calculate the time? what if you need to go 5 miles and you're going 25 miles per hour? Yeah, we need to take this and divide it by 4.33, like that. So the time that it takes to open up is 0.363 seconds. Not too long. The final example problem that I wanted to show you today was about a neutron star, my favorite. We've got this beautiful artwork of a collapsing core of a dying star. This collapsing core has a radius initially of 300,000 kilometers and a mass of 10 to the 30th kilograms. And stars like our sun rotate about once every 30 days. A neutron star is formed when a supermassive chunk like this of the core of a dying star collapses down to be 6 kilometers in diameter, in radius, I mean, instead of 300,000 kilometers in radius. Doing so is just like the figure skater who tucks in her arms to spin faster. When you collapse something like that, it's like tucking in your arms and spinning faster. We can expect this neutron star to start spinning a whole bunch faster because its radius has declined by a whole bunch. What kind of problem is this? This is a conservation of angular momentum problem, as one would hope. Delta L is equal to 0. Now there's no collision happening here at all. The only thing that's changing is the radius of the star. L initial is equal to L final. The angular momentum of the core of the star initially is going to equal the angular momentum of the core of the star afterwards. But afterwards, we're going to call it a neutron star instead of the core of the original star. If you want to learn more about that, take my Intro to Space Science course. L initial, well, as usual, it's going to be I omega. There's nothing like coming in to hit it from the side, so we don't have to deal with R cross P. So I omega, I initial, omega initial, is equal to I final, omega final. Well, what is the moment of inertia of a solid sphere? Moment of inertia of a solid sphere is 2/5 mr squared. And this is R initial times omega initial. And that's equal to 2/5 mr final squared omega final. The neutron star is still a solid sphere at the end. This right here, this line right here, is one reason that I always think that you should write everything down as symbols, like as algebra, before you plug in any numbers. Because if you started plugging in numbers here, you'd then have wasted a huge amount of your time because you can totally get rid of that with that, and can get rid of that with that. That fraction out there didn't matter, and that mass didn't matter. If it was 1 kilogram or a billion kilograms, then it still didn't matter. All we have is initial radius, final radius, initial angular velocity, final angular velocity. Well, I guess we need to figure out what the initial angular velocity is. We know that it rotates once, so one rotation every 30 days. We should probably get this into radians per second. So one rotation is 2 pi radians. 1 day is 86,400 seconds. There's a country song about that, I'm pretty sure. 86,400 seconds? I don't know, somewhere in my brain. So let's figure this out. 2 times pi divided by 30 times 86,400 gets us initial angular velocity of 2.42 times 10 to the -6 radians per second. Not very fast. We can plug this in. Radius initial was 300,000 kilometers. Should I be doing something with that? Yeah, I should. Making it into meters. Squared times omega initial, 2.42 times 10 to the negative 6 radians per second is equal to the final radius, 6 kilometers or 6,000 meters squared times omega final. We can plug this into our calculator and solve for omega final. 300 times 10 to the 6, all that squared, times this original thing divided by 6,000 squared gives us omega final of 6,057 radians per second. Is that fast? Well, we should probably convert that to revolutions per second, I guess. So we can say that there are 2 pi radians in 1 revolution. So this divided by 2 times pi. Now notice what I did in my calculator. If you can see that, I put parentheses around the 2 times pi. I know a lot of students will forget the parentheses. If you forget the parentheses, your calculator will divide by 2 and then multiply the entire thing by pi. We don't want that. We want to divide the whole thing by 2 times pi. So put those parentheses around there. Okay, we get 964.5 revolutions per second. Oh dear, that is really spinning fast, almost 1,000 times per second. Many neutron stars can spin at about that rate, and that's just wild. That's how we discovered them, and maybe we can talk sometime about neutron stars in general, but it's a fascinating thing to think about and to research about. So, keep studying this, keep learning about angular momentum. Good luck.